Howdy, and welcome back to the Austin Earth Science Zoomerama. Today's presentation is by staff at the Texas Water Development Board. We have Natalie Ballew, Shae Luther, and Josh Sendejar in their presentation entitled The Secret Life of Groundwater.
Well, hello to everyone out there in your virtual classrooms. As Linda said, this session is about groundwater and how we can learn more about its secret life underground. Now, groundwater has often been perceived as a complete mystery. Imagination and mythology used to drive the perceptions of groundwater flow. What you see here is an image actually from the 1600s, and this is how people used to understand the way that groundwater flowed around the earth. Back then, people believed that water moved from the sea floor through these mysterious channels underground and up into mountains, where then the groundwater was discharged as springs. Even in the Texas Supreme Court in more recent history, groundwater has been called secret, occult, and concealed. But now, based on scientific observation, we have the water cycle as we know it today. And I'm sure you're all familiar with the water cycle, how water moves around the earth and the atmosphere. The basics, if you need a refresher, are evaporation, condensation, and precipitation. But the water cycle is so much more than just that. Scientists continue to collect data to understand all parts of the water cycle because it's essential to life on Earth. And understanding all parts of it can help us make smart decisions around the use and conservation to ensure that we have water available for generations to come. So today we're going to focus on the groundwater portion of the water cycle. In Texas, groundwater is an essential water resource for us. We use it for things like irrigation, public water supply, environmental needs, and in fact, there's more groundwater use in the state than there is surface water use. And groundwater is a resource that you can't see very easily, which makes it a little difficult to study sometimes. You can really only see evidence of groundwater when you start digging holes in the ground or start to get curious about water that's bubbling up from the land surface. So here I'm going to show you a video of a spring. And so if you focus on just to the right of that equipment, you'll see water that's bubbling from the land surface. And so what you have here is groundwater that's actually flowing from beneath the ground, and it's traveling along the land surface and then contributing to the nearby river. And the people that you see in this video are actually out there taking measurements of the spring so that we can understand how much it contributes to surface water. And here we have examples of water seeping through sand and dirt and rocks while digging holes in the ground. On the left here, we have an example of a hole that's dug on a beach. And if you've ever been to the beach and you started digging through the dirt, you might have noticed that eventually it's going to start filling up with water. And that right there is an example of groundwater flow happening right before your eyes. On the right here, we have a well that is being hand dug by these people down here in the bottom. And this is a pretty big hand dug well. And so they had to go through all of this dirt before they get to the bottom. And you can actually see a little bit of water down there at the bottom. So they have reached groundwater now, and they'll probably keep going a little bit more so that they can fill up their well with some groundwater. So after you've dug your well, or if you've drilled a well, you can see groundwater as soon as it's pumped out of a well. So here on the left, we have an example of a hand pump. So you start maneuvering this lever and the well pulls water up from the ground and deposits it in a bucket, which then you can use it. And you can also see groundwater sometimes just flowing right out of wells. This example here, you just see groundwater spurting up out of this well. And I'll explain how this kind of flowing wells happen a little bit later. So you can't actually see water in this well. This is kind of just more of a fun example. This well here is called the Big Well, and it is in Greensburg, Kansas. It is the biggest hand-dug well in the United States, and that's hand-dug. This well is about 30 feet wide and about 100 feet deep. And I think 100 feet is about 10 stories or so. So just look at the stairs in this example, and you can get an idea of how big this well really is. This well used to be used as a water supply until about the 1930s, but now it's a big tourist attraction in Kansas. And I would guess that the bottom of it is just filled with a bunch of loose change and lost iPhones. And a fun little fact, it's considered one of the 8 wonders of Kansas. So if you're ever on a road trip in Kansas, go check it out. So we know groundwater exists because we've dug holes in the ground and see the water. But how do we find it? Back in the day, folks usually relied on magic to find groundwater. The technique that's used for that is called dowsing or water witching. And it's traditionally done with a wishbone-shaped tree branch that's held in 2 hands, like you can see in these 2 images. And as people would walk across their land, they'd hold their tree branches. And if the branch started to pull downwards to the land, then that was a signal that there's water beneath their feet. Now, this is not a scientifically proven technique, but it is still a method that farmers and ranchers and water well drillers use to find water. But understanding how and where to find groundwater is not magic. It's certainly not Magic the Gathering, if you're into that game. It is science. So studying geology and hydrogeology helps us to understand how groundwater is stored in and moves through an aquifer, and can help us understand how the impacts that we have as humans can influence our groundwater resources. So I just use a term called aquifer. So what is an aquifer? Aquifers are essentially dirt and rocks, or what we call geologic formations, that are filled or saturated with water. So aquifers are water-bearing rocks that are beneath the land surface. And the official definition in the United States is a geologic media that can yield economically usable amounts of water. And aquifers are formed very, very slowly over time. You got to think on a geologic time scale whenever you think about how aquifers are formed. And so they're formed slowly over time, and they're slowly filled up when rain falls and seeps down into those rock formations. And then when the open space in the rock formations becomes saturated with water, it then becomes an aquifer. So now I'm going to introduce you to 2 terms that are very important in understanding the ability of an aquifer to store and produce water. The first is porosity. Porosity is the measure of the volume of empty space inside the rock, and it represents the volume of water that a rock formation can hold. So imagine that this little diagram here is a close-up of a rock. You have all of your individual grains that are touching one another, but there's some, because of the shape of your grains, there's some open space where the grains don't actually touch. And we call these pore spaces. Sometimes if it's an unsaturated rock formation, those areas are filled with air. But if you're in a saturated formation or an aquifer, those pore spaces are filled with water. And the second term is permeability. Permeability is a measure of how easily water can flow through a rock. So you have the same concept with your little grains and you have your pore spaces still, but permeability is essentially how interconnected those pore spaces are. So permeability is essentially the way that water can travel through the pore spaces within a rock formation. And so you have these little flow channels that water can move through within a rock. So these next 3 slides are some examples of aquifers in Texas. And of course, these are not like underground photos or anything. These are pictures of the unsaturated parts of the aquifers. And these are the rock formations as they are exposed on the land surface. And that's what we call in geology outcrops. So these are outcrops of the aquifers. So this first one is the Hickory Aquifer. And the Hickory Aquifer spans across much of central Texas. It is a sandstone aquifer. And so what you see here is a rock that is composed of sand grains that have been pushed together and kind of glued together over time. And so there exists some pore space within this sandstone rock. And you can see too here in this picture, there's a big old fracture that's going right through this rock. And if you imagine this rock underneath the ground and it was saturated, this would be a great channel for water to actually flow through the rock. And it would be an indication of some permeability within the rock. And here we have the Edwards Trinity Plateau Aquifer. This is a huge aquifer that spans across basically central Texas all the way to West Texas. And if you can tell that the color is a little bit different than that first aquifer that I showed you. The texture is a little bit different of this aquifer. And that's because it's a different type of rock. This aquifer is composed of limestone primarily. And so it has a little bit different porosity and permeability characteristics than a sandstone aquifer would. And you can actually see groundwater coming out of this aquifer here, or this rock formation. So here you see some water seeping along this plane right here. And if you look up here a little bit higher, you can see some plants that are kind of growing out of this line in the rock. And plants need water, so there's definitely water coming through that little area of the formation. And here's a third example of an aquifer. This is the Ogallala Aquifer, one of the largest aquifers in the world, and it is composed of sand and gravel. So that first aquifer was sandstone, and it was a rock that's formed from sand grains being glued together. But this, you can see that the texture is a little bit different in the way that the rocks are crumbling down the side of the cliff edge here is a little different than that sandstone aquifer. And that's because it's mainly it's a looser sand and gravel. And you can see too that the color is a little bit different, and it's just a different type of aquifer. And this is a picture that was taken near the entrance of Palo Duro Canyon State Park. And if you haven't been there, I would highly recommend to convince your family to go out on a trip there, because there's some beautiful things to look at and some really fun hikes that you can take and see some cool geology. So there are two different types of general aquifers. We have unconfined aquifers and confined aquifers. So an unconfined aquifer is an aquifer that is bounded on the bottom by a confining layer, but is not bounded on the top. So your bottom part of the aquifer is a relatively impermeable rock formation. So water cannot easily flow through the confining layer. And then above that, you have the saturated portion of the whatever geologic formation you have, which would be called the aquifer. And then you have the unsaturated portion of that formation above that. And if you were to drill a well in an unconfined aquifer, water would slowly fill into that well, and you would eventually see the water level within your well that would be the equivalent of what we call the water table. So that's essentially the top of the saturated portion of the aquifer. Now, when you start pumping water out of your well, what you're going to see is a decline in the water level. So your water level used to be up here where the water table was, but now since you've been removing water from the formation, your water level is dropping. And so see the shape here, it takes a long time for that pumping to be reflected in other parts of the aquifer because of the porosity and permeability characteristics of that formation. And so you will see more evidence of that water level decline closer to the well than if you're further away from the well. And what we call this is the cone of depression. And that's that kind of decline towards the center of the well. And this is one of my favorite terms in hydrogeology. The way that I remember it is if you were like doing something bad and you get sent to the corner and you had to wear a dunce cap, you're just kind of sad and you're in the corner wearing your cone of depression, but just flip that upside down. So that's how I remember a cone of depression, if you ever need a way to remember that. So a confined aquifer is similar to an unconfined aquifer. It has a confining layer at the bottom, but there is also a confining layer at the top. And whenever you drill a well into a confined aquifer, your water level actually rises above the top of the aquifer. So here's the top of the aquifer, and your water level actually rises above it. And the water level, if you were to extend it all across the kind of top of the aquifer, we call that, instead of the water table, we call it the potentiometric surface. So it's a little different than an unconfined aquifer, but similar concept. And a way that you can imagine what's happening in a confined aquifer is if you were to fill up a Ziploc baggie with water completely. And then you lay your Ziploc baggie on the table, and then you take a straw, you put your thumb on top of the straw, and you jab it into the Ziploc bag. And whenever you do that, you would see the water within your straw kind of rise up above the top of the Ziploc bag. And then if you were to release your thumb, water would more than likely spurt out the top of it. And so that's how that first well that I showed you towards the beginning, where water's just flowing out of it, that comes from a confined aquifer system. And we also call those artesian aquifers. So that's a fun little experiment that you can try at home to demonstrate a confined aquifer. And so similar to an unconfined aquifer, when you start pumping water out of your well, the water level will begin to decline, and you will see a similar kind of cone of depression in the potentiometric surface of a confined aquifer. Now, oftentimes there are multiple types of aquifers in any location. As you can see here, we have a system with an unconfined aquifer, and then we have two confined aquifers beneath that. You can also see in this diagram the time that it takes for groundwater to move underground. It can vary from days all the way to thousands of years. And so this diagram here shows a scene mainly uninterrupted by humans. But you know, we have all sorts of infrastructure and other things going on at the land surface that could impact our water supplies. One example is homes that have septic systems. So the waste that's produced, from toilet use is stored in a tank underground. And if that's not constructed properly, you could have a potential for leaks and then contamination, especially if you have a well near your property that you use for your water supply. That could be a potential contaminant source. We also have ranching and farming, and some of the byproducts associated with those practices can end up in groundwater and can even run off into surface water. We also have urban development. The very nature of all the concrete and the things that run off when it rains from our sidewalks and our streets can eventually end up in groundwater supplies or surface water supplies if everything isn't designed with that kind of thing in mind. And we also have the impacts of cars. Sometimes you get oil spills from cars. Also related to cars, you have gas stations that usually have underground storage tanks for their gas supplies. And sometimes if those aren't monitored or taken care of properly, those can get into your groundwater supplies. So understanding an aquifer and how it behaves can help us understand what happens when contaminants or pollutants get into our groundwater and what we can do to prevent or remedy the situation. And there are a lot of jobs in that field, remediating contamination. So if that's something you're interested in, definitely explore that field. So now we're going to get into an activity about point and non-point source pollution impacts on aquifers. But before we get to that, I just wanted to mention that at the end of my slides here, I have a couple of resources that will also be available on our Zoomerama webpage. There are just some links to some videos and additional educational resources that could be useful to you. So now I'm going to turn it over to Josh Sendejar and Shae Luther to get going with our activity.
Thanks, Natalie. Okay, so Natalie just told you about what an aquifer was and kind of how they work. And she mentioned how we as humans can pollute those aquifers. But because they are underground, it's kind of hard to see when they're polluted like we can when there's rivers and lakes are polluted. And it's very hard and very expensive to clean them up because once the water's polluted down underground, first we got to know it's polluted. And then once we know it's polluted, how do we get to it to clean it, which is very hard to do. So we're going to do an easy activity that uses everyday items to show you how different things may pollute groundwater. Natalie showed you in the slide, but we're gonna actually show you things you can do at home and test it. So we're gonna use everyday materials like a disposable aluminum pan. In this case, we're just gonna use the clear top because you wanna be able to see underneath and what actually happened in the aquifer. We're also gonna use, for my scenario, we're going to use paper towels. That's going to act as the aquifer. Aluminum foil. I'll explain why here in just a moment. We're going to use sand and gravel, which will form the upper layer of the aquifer. We're going to use water because we got to make it rain. Because in my point, I'm going to use non-point source pollution in my activity so that you can see how things that just land on the ground randomly, when it rains, can wash over ground and eventually infiltrate down into the aquifer. And then for pollution, we're going to use a powdered drink mix, and it will act as the pollution because once it gets wet, you'll be able to see it underneath and how that impacts the groundwater. And then for fun, because of what I'm going to do, we're going to use these little Matchbox cars. So give me just a second. I need to switch to a different camera so you can see what I'm doing. And there we go. Okay, so here is, let me move this out of the way. So here's our clear lid. It's going to act as the base of our model. And then we're going to line it with the paper towel because the paper towel is porous and has permeability and porosity, just like Natalie described, because the weave of the paper towel is going to allow things to move through it. And then we are going to layer the gravel, and you can do this however you want. You can stack it up higher at one end, you can lay it out straight. That's the fun thing when you're doing experiments at home. You can try all different things to see how that affects the impact. But always try to guess at what's going to happen. That's called a hypothesis. And then you can see if what you guessed actually works or happened. And if not, then you can figure out why. So now we have our rock. And so in my scenario, a big box store such as Walmart or grocery store or Target bought a plot of land that used to be a farm. So there was nothing built on it. They came in and they built their store, but they also had to build a huge parking lot. And so our aluminum foil is going to play the role of our parking lot. So half of the lot is covered because we all know how big the parking lots are at stores. So there's our parking lot, and here's our cars parked on the parking lot. Well, the cars are a lot bigger than the lot, but we're going to pretend. So one of these cars has a leak, and it's leaking oil onto the parking lot. So we are going to take our drink mix, and other cars come and go. Other cars leak. Not all cars leak. Some do, some don't. But we're going to sprinkle our drink mix onto the parking lot, because if you've ever seen driveways or parking lots from cars that leak, you see dark patches. So now we have our pollution on our parking lot, and we're going to make it rain. What happens when it rains? So here we go. I have my water bottle. I don't know if you can see it. There you go. So we're making it rain. So we have a big storm, and it's starting to gather. You can see how the rain, and you've seen rainstorms, how water flows across sidewalks and parking lots and driveways. And as it rains, it runs and can run across the ground and get into local streams and pollute surface water, but it can also pollute the groundwater as it infiltrates down into the ground. So our rainstorm ends, and then sometimes it takes a while, like Natalie said, it may take days, it may take years to get down into the groundwater. But what happens once that does? I'm gonna have to pick up the tray so I can show you underneath so we can see how or if it impacted the aquifer. So give me just a minute because I'm gonna have to make a change. Let's see if it turned red underneath. Oh, it started to. Oh, my hand's in the way. Okay, let's try it like this. There we go. Can you see? So if the paper towel is the aquifer and the red drink mix was the pollutant, you can see in this case how it drained down. And since we're using gravel and sand, we'll pretend it's the Ogallala, as Natalie described it. So it's a little bit looser gravel and sand. How it seeped through the gravel and sand and made it down into the aquifer. Well, think if that happens on all of the parking lots of all of the stores in your town, what would you do then? So this is an example of non-point source pollution because as the water rushes across the ground, it picks up stuff as it goes and it gets into surface water and groundwater along the way. Point source pollution, you can pinpoint to one specific location that it's coming from. And I'm going to turn it over to Josh and let Josh explain to you his scenario and how point source pollution affected his aquifer.
Hi, everybody. So for my scenario, we're going to look at point source pollution. And like Shae said, we can tell where point source pollution is coming from. So for my scenario, I'm going to move my camera a little bit. We have this tanker truck. And this tanker truck is driving along a country road. All of a sudden, a deer pops up in front of his truck. And so he swerves to try to avoid it, and he ends up turning over and wrecking into a ditch off the side of the road. Now, this particular tanker truck is carrying fuel, so gasoline, oil, something along those lines. And so he is leaking that oil into the ditch that he crashed into. And so I'm going to make one more change. And we can see, unlike how much time needed for that parking lot in Shae's example, we see in this particular aquifer, it's happening very quickly. That pollution is spreading. And if we had another rain event, like in Shae's example, that pollution would spread even more. And so again, in Shae's example with the parking lot, we don't know exactly which car made that pollution. But in this example, we know this tanker truck is our source of a pollution. We can pinpoint the source, and that is why we call it point source pollution. And so as Shae said, there are a lot of different ways you can adapt this. You can make different scenarios that will fit in your neighborhood. Natalie brought up the example of a septic tank. That's another thing that you could kind of play with and see. But there are a number of different ways that you could use to make some obscure concepts like the idea of an aquifer become a little more real in how we can affect those environments.
That is great. Thank you very much. I love those examples, the presentation and the hands-on, and I appreciate that. You guys did a great job. And I encourage students to work with sand and gravel and rocks and water. One of the famous professors I had at the University of Texas when I was an undergraduate took the class out to a sandbox with a water hose to play with these things. So it's a good break from being connected to the computer screen. You can find these things easily around your home and watch how the water drains through the rocks, move the rocks with the water. I love the experiments with contamination that you use to see. It shows you how the water flows. It traces it, just like hydrogeologists use dye traces. So those are all great. Thank you. And we will be sharing this on our websites. Before we go forward to show you that, though, part of our goal with this program is to encourage students to consider working in the geosciences, which is a very broad area, as you'll see if you watch our Zoomerama. Can I ask you guys to just tell us a little bit about how you found your career path into water resources? Natalie, would you like to start?
Sure. So whenever I was in school, all throughout school, I loved math and science. I also loved art. Those are my kind of two big things that I was into. And once I got to college, I had no idea what I wanted to do. But I took a geology course. And I was like, oh my goodness, I can use math and science in this. And I can also kind of use my creative brain, because geology, you really have to kind of understand and be able to think in 3 dimensions. And so that kind of like imagination of the mind and stretching to envision how things are working underground was really appealing to me. And so I also learned from that geology course that geologists spend a lot of time outside, and I love to go camping and I love to, do hands-on things all the time. So it was just a perfect fit to be able to use my skills in math and science, and then to explore it in the geological world. And then I got interested in the water resources side of things because I really saw how important understanding our water resources and securing those supplies for our future, just how important that was. And so I work for the state, I'm a public servant, and that just really called to my soul in some ways. But that's kind of how I ended up in the water resources field.
Ah, great. You combine things that you loved and service. That's wonderful.
Mm-hmm.
Shae, how about you? Tell us about your story.
So like Natalie, I figured mine out in school, but mine was a little later. When I first started college, I went to community college first, and I was not into math or science. It was just classes that we had to take to finish part of our degree. But during that, I was in a biology class and I did an honors project. And part of that honors project was where I went out and took water samples to local creeks that didn't always run all the time. Some did, some didn't. And we counted the macroinvertebrates, like the larvae to dragonflies and any kind of bugs that were in it. We had to identify them and count them. And you could use part of that to gauge how good or bad the water quality was, depending on what kind of bugs was in it. Well, that always stuck with me, even though my degree at that time had nothing to do with math or science. It was history. Mm-hmm. So I finished that degree and moved on. And later in life, a little bit later, I was looking for a graduate degree, and I kept returning back to that water project I did in that biology class. And I knew I enjoyed working with water. I wasn't really sure how, but that kind of is what got me on the water path. And I ended up in conservation and working for a city in their conservation department. And then from there, I moved to the States working in water conservation. So in an area in school that I didn't think I would do anything with, one little project caught my interest. And that, unbeknownst to me at the time, is what shifted my gears later in life and got me into water. So.
Oh, that's fantastic. They often say that if you're a teacher, you never know the impact you might have long-term on your students. Sometimes one experience, one comment even.
Right.
That's great. Josh, how about you? Tell us about your path.
So I was born and raised in Corpus Christi along the coast, and I have always been fascinated by the ocean and marine life. And very early on in my childhood, I took a visit to my local aquarium. And it was amazing. It was, the 90s. This aquarium was not as big as it is today. And because of that, I could kind of run wild. And my parents, my teachers didn't have to worry about where I was. I could just kind of let my curiosity just flourish. And that sort of carried on into school. I was very curious about science, about, those different ocean animals that I had learned about. And when I went to college, I wanted to do marine biology, and I ended up taking an environmental science course as part of that. And oh boy, that changed everything for me, because instead of just the ocean, it was like the earth was this big puzzle. And with environmental science, you learn a little of the biology, you learn a little of the chemistry, the geology. I took a meteorology course as part of my undergraduate degree. All of these different things became little pieces that I carried with me and got to put together this puzzle. And in graduate school, I took a course specifically on water resource issues. And so we learned about things like pollution within the activity that we just did. We learned about things like hypoxia, which happens in our oceans. And that's when it really clicked for me that I wanted to make a career out of water resources. And so the first job that I got out of graduate school was in environmental education. And so I worked at a nature preserve where we got to see between 8,000 and 10,000 students, like many of you at home. And I got to kind of take them around and be outside, as Natalie talked about, and kind of show them all the cool things that nature had to offer on my particular preserve. And then after about 2 years in that position, I joined the Water Development Board. And what brought me here was working with the Water Conservation Advisory Council. It's like all those different pieces of everyone who uses water and why. And I got to learn their different perspectives, why their resource or their interest is important. And it just helped me further develop that puzzle of water in Texas.
Oh, I love that. Thank you. Thanks so much for sharing. It's an interesting process. And I hope this is like passing the torch to the next generation, that you guys have come, and thank you for sharing your stories. I think this is something good. We encourage you students to explore these great earth science topics. There's a variety of things. There's room for a lot of creativity, and there's relevance to today's world. Now, before we leave, I was hoping we could just point out to you where you can find the directions for some of the experiments you saw today, and also other great resources that the Water Development Board has. Of course, we have this presentation and links are on the Austin Earth Science Zoomerama webpage for the Secret Life of Groundwater. But the Water Development Board also has a page. Josh, would you like to show us that, the TWDB kids?
Absolutely. So I'm going to share my screen. All right. So this is our Texas Water Development Board kids page. And if you see up top on where it says home, if you were just to land on our website, how you would get here is you would move over to conservation. And toward the very bottom, there's education. There's conservation education as one of the links down there in that last paragraph. There we go. And so this brings us to conservation, and then you have TWDB kids in that right-hand toolbar. Yeah. It's a little confusing, I apologize,
yes.
But that's why we're kind of going through it with you guys here. And so we have a number of resources that are available for a wide array of different levels within education. There are K through 12 resources available here. And if you scroll down a little further, our Major Rivers program is our 4th and 5th grade program that kind of covers some basic terminology in terms of watersheds and also introduces some conservation concepts. Raising Your Water IQ is actually where the activity that we did today comes from. And there are several different activities that you can create and replicate in the household using some basic everyday supplies like we use today. And then if you scroll down a little bit further, there are some physical model videos that are actually from our groundwater department where Natalie is from. And they use a groundwater model and talk about how different areas can become polluted and how that pollution may travel in different environments. There are some interactive games that are a part of our website. And then water exploration is our high school-based curriculum, and it operates on legacy cycles. Each cycle might talk about a different topic based on water, whether that's pollution or some other subject. And then finally, we have our kids coloring book, which is kind of our K through third grade resource. And it provides, again, some facts on conservation and water.
That's great. You hit really the full K through 12 spectrum on the TWDB kids. So it's not just for younger grades, you go all the way up through high school. So that's wonderful. Thank
Absolutely,
you.
yeah.
Well, I guess with this, I'll say thank you again very much for joining us in this Zoomerama presentation. And for those of you watching on YouTube, if you have a question we didn't answer, leave a comment below and we'll do our best to get an answer to you. Also, check the description on the video links to more information on our website. And don't miss our next talk with Troy Kimmel and Bob Rose on wild weather in Central Texas this Thursday at 10 a.m. Central Standard Time, and soon after that on YouTube. Thank you very much. See you next time.